Hi all, I am going to take the seminar on the topic some problems that cannot be solved by Turing machine, which is the limit of algorithmic computation. Here we are discussing about Turing machine, limits of algorithmic computation, halting problem, and then some theorems associated with it. Turing machine is a mathematical model and it is used to accept recursive enumerable languages generated by type 0 grammars. There are few limitations to the power of a Turing machine. That is, there is some problems that cannot be solved by Turing machine. That is we are going to talk about. Before going through our topic, we should know about Turing machine. Turing machine is a mathematical model which was invented by Alan Turing in 1936. It is used to accept recursive enumerable languages generated by type 0 grammars. Recursively enumerable means if there exists a Turing machine that accepts every string of the language and does not accept strings that are not in the language. It consists of a tape of infinite length on which read and write operation is performed. So there is unlimited memory for a Turing machine. A problem that a common computer can solve will also be solvable using Turing machine. It can simulate any computer algorithm. Limits of algorithmic computation. There are few limitations to the power of a Turing machine. On several occasions, there could not exist any algorithms for the solution of certain problems. Some problems that cannot be solved by Turing machine. There are questions that can be clearly and simply stated with an apparent possibility of an algorithmic solution but which are known to be unsolvable by any computer. We first define the concept of decidability and computability to pin down what we mean when we say that something cannot be done by Turing machine. Then computability and decidability. A function on a certain domain is said to be computable if there exists a Turing machine that computes the value for all arguments in its domain. A function is uncomputable if no such Turing machine exists. When we classify a function as computable and not computable, we must be clear on what its domain is. Our concern here will be the result of a computation is a simple yes or no. In this case, we talk about a problem being decidable or undecidable. A problem is decidable if there exists a Turing machine that gives the correct answer for every statement in the domain of the problem. A problem is undecidable if no such Turing machine exists. So we should have more clear about decidable problem. A problem is said to be decidable if there exists an algorithm which can solve the problem in finite amount of time. Here we can see an example that we are constructing finite automata that accept all strings A and B where each string starts with A. Then Q0 is the initial state. Getting A from Q0, we get a new state Q1 which is the final state, and from Q1 any combination of A and B are accepted. So the string is accepted in this case. But in case of getting B from Q0, it goes to dead state and it will be rejected because only the string starting with A should be accepted. So here we can see a decision on halt that is accepted or rejected. And we can also create an algorithm which can solve the problem in finite amount of time. So this problem is decidable. Then we can see the halting problem which is occur due to undecidability. Halting means we are stopping the problem. The output of Turing machine can be halt or no halt. Halt means the machine will halt state, accept or reject state after a finite number of states. No halt means the machine will never reach the halt state, that is accept or reject state, no matter how long it runs. Here we are asking a question. Can we find a program that can predict whether any other program will halt or run forever? This is known as halting problem. That is it possible to tell whether a given machine will halt for some given input or it run forever infinitely? For an example, in pseudocode, the program while true then continue does not halt, rather it goes on forever in an infinite loop. On the other hand, the program print hello world does halt because it prints only once and then terminated. There are two theorems. The first one is there does not exist any Turing machine that can make a correct decision for a particular input. The halting problem is therefore undecidable. It can be proved by contradiction. There is an input string and we have to find, does the Turing machine finish computing of the string in a finite number of steps? The answer must be either yes or no. Because it is undecidable, we cannot able to tell whether it complete the string in a finite number of steps. So the answer can be yes or otherwise no. Then assume the Turing machine exists to solve this problem, and then we will show it is contradicting itself. We will call this Turing machine as a halting machine that produces yes or no in a finite amount of time. If the halting machine finishes in a finite amount of time, the output comes as yes, otherwise no. In this block diagram of halting machine, we giving an input string W and halting machine produce yes or no in finite amount of time. Yes means the halting machine halts on input W and no means halting machine does not halt on input W. So it's just taking an inversion of halting machine. These are the condition for that. If H returns yes, then loop forever. If H returns no, then halt. So the diagram for inverted halting machine is this. Just we are taking the input string and the halting machine produces yes or no. As the condition, if halting machine returns yes, then loop forever. We can see the two states are in the infinite loop. Whenever it no means halt. Here we have got a contradiction because it is not possible. Hence, the halting problem is undecidable. We have another theorem to discuss. Before going to that section, we should clearly know about recursive and recursive enumerable languages. Recursive enumerable languages. An RE language can be accept means it will enter into a final state for the string of language and may or may not enter into rejecting state for the strings which are not part of the language. It means Turing machine can loop forever for the strings which are not a part of the language. Then for recursive language, a REC language is a subset of RE can be decided by Turing machine, which means it will enter into a final state for the string of the language and rejecting state for the strings which are not part of the language. Here the main difference is the recursive language always halt whether input string is accepted by the machine or not. But in case of recursive enumerable language, it only halts for input string which are in the language. Okay. So we can say that recursive language is a subset of recursive enumerable language as shown in this figure. That is, every recursive language can be recursive enumerable language, but not vice versa. Theorem 2. If the halting problem were decidable, then every recursively enumerable language would be recursive. Consequently, the halting problem is undecidable. For a proof, let L be a recursively enumerable language on epsilon, and let M be a Turing machine that accepts L. Let H be a Turing machine that solves the halting problem. We construct from this the following procedure. If halting machine says no, that is halting machine is not halt or undecidable, then by definition input string W is not in recursively enumerable language. Our theorem is if the halting problem is decidable, then it accepts every string in the language. We got that H says no, that is undecidable, then it does not accept every string in the language. So the input string is not in the recursively enumerable language. If H says yes, that is halt or decidable, then it is a Turing machine. Then the Turing machine must halt, that is it should have a solution that is yes or no. So it will eventually tell us whether W is in L or not. But we already know that there are recursively enumerable languages that are not recursive, because every recursive language can be recursive enumerable language but not vice versa. For an example for recursive enumerable languages that are not recursive is universal languages. Okay, then the contradiction implies that H cannot exist, that is that the halting problem is undecidable. Reducing one undecidable problem to another. Reducing or a reduction is a way of converting one problem into another problem such that a solution to the second problem can be used to solve the first problem. A theorem for that is a problem A is reduced to a problem B if the decidability of A follows from the decidability of B. Then, if we know that A is undecidable, we can conclude that B is also undecidable. We can say that first problem reduces to the second problem. So, if the first problem is undecidable, we can say that second problem is also undecidable. Here is an example. Measuring the area of a rectangle reduces to measuring the length of the sides, which means by the solution of measuring the length of the sides used to solve the problem measuring the area of the rectangle. For a conclusion, Turing machine is a mathematical model and it is used to accept recursive enumerable languages generated by type 0 grammars. Here is a question. Can we find a program that can predict whether any other program will halt or run forever? This is known as halting problem. There does not exist any Turing machine that make a correct decision for a particular input. The halting problem is therefore undecidable. Here is some questions. Thank you.